This is chapter 6.4. We are continuing. We have an example of a frame on the screen, and we have points. This is point A. Then we have point B and point C. So I'm going to come in here and label my diagram. AB. This is also point B. Actually, I'm going to move that down just a little bit. And this is point C. So as we can look at this, we see that this is one piece. And so we can pretty much come in and say this is a two-force member right here. So if I came in, I could draw a two-force member like this, and I can name these force BC. And again, they are opposite and equal. We could also break those two forces up as so, and we could call this CY and CX and BY and BX. If we were to go to look at B, the two force member would be opposite and equal, so we'd actually draw it as so, and we would draw it again like so. We also have this distributed load, so let's put the distributed load in green. So the distributed load is going to act here, which is going to be 1 meter from this side, and it would be 400 Newton meters times 3 meters times 1/2, which comes out to be 600 newtons. And then at our pin we have AY and AX. And then we could start solving for whatever we needed to solve for. This is just a free body diagram example, but this would help you to get going on solving for reaction forces, members along AB, or members along BC, or maybe all forces acting on the frame. Now, let's go ahead and go to our second example. Okay, so here's an example, and it's actually F6-23 in the book. If you notice, I have already drawn the free body diagram. I have broken it up into members AB, member AD, which is a two-force member. If you notice, I've already drawn my two forces coming off each end. Also, B is a two-force member, and I did the same. And then I have member EDC, BC, and BC here. So you could say that we could also call this BY, we could also call this CY, so we can also say that BY is equal to CY, looking at this two-force member. There are no X components at B and C due to the two-force member. We have a distributed load, which I've already broken up, 3 kilonewtons, 3 kilonewtons, and it is 1 meter away, since that it would be 2/3 of 1.5, which would be 1 meter. So each one of these sections here would be 1 meter in distance. Here, this is in the middle of the beam. Doesn't look like it, but it's in the middle. It's 1.5 meters and 1.5 meters. We also have, so I'm going to do this. I'm going to label this as 5 kilonewtons, and I'm going to label this down as BC. That's just a little easier to look at. Okay, and what we're asking us to do is to solve for the reaction at E. So by looking at member AB, I can sum my moment about point A. And this is how I'm thinking I'm going to tackle this problem. If I sum my moment about point A, I will get point BC. Once I get BC, I can transfer it by looking at member BC, and it's going to be the same down here in that going in a downward direction. Then I can come over here and look at EDC, sum my moment about point E, and I will be able to get AD. Then I'll be able to sum my forces in the X and Y along EDC, and I would be able to get my reaction forces there. So if I sum my moment about point A, I get 3 kilonewtons times 1 meter minus 3 kilonewtons times 2 meters plus BC times 3 meters. So I'm looking at member AB here. It's all equal to 0. BC comes out to be 3 kilonewtons. Now if I sum my moment about point E, looking at member EDC, I am going to get AD. Now when we looked at AD, we can say that this is going to be a 1.5 to 2.5. You could also look at it as a 3, 4, 5 triangle, but I'm going to use the 2 and 2.5. So AD times 2 over 2.5 times 1.5 meters minus 3 kilonewtons times 3 meters minus 5 kilonewtons times 3 meters is all equal to 0. So using this, punching this in my calculator, I get AD is equal to 20 kilonewtons. So now I can sum my forces in the X, still looking at EDC, remember EDC, and I can sum my forces in the Y to get my two reaction forces. So if I sum my forces in the X, I get EX, I'm showing it in a positive. AD came out to be positive, so its direction is correct, so I could say minus 20 kilonewtons times 1.5 over 2.5, breaking it into its component, is equal to 0. So EX comes out to be 12 kilonewtons. And sum my forces in the Y, I get EY plus 20 kilonewtons times 2 over 2.5 minus 3 kilonewtons minus 5 kilonewtons is equal to 0. So EY comes out to be negative 8 kilonewtons, or 8 kilonewtons that is going down. Alright, I'm going to be doing one more example, and we'll see how this goes. If you have questions, please post them on the discussion page. Thank you.